we've talked briefly about the concept of analogues, in that heroin is an analogue of morphine, and that atropine, for instance, is also an analogue of morphine. So here's desomorphine. It's made from morphine, it's more potent than morphine, but it's not readily available to illegal users. On the other hand, here's codeine. Codeine may be made from morphine, or it may be extracted directly from opium. And codeine in most countries is relatively easy to obtain because it's used in cold medicines. It's nowhere near as active as morphine, and so in many countries, codeine-containing medicines are available over the counter. You can convert codeine to desomorphine. You need to remove one carbon atom and one oxygen atom and add a few hydrogen atoms. One way to do this is a recipe that's available on the street, which is to treat codeine with iodine, red phosphorus, hydrochloric acid, and a solvent such as gasoline or oil. Now, iodine, of course, you can easily get from pharmacist's shop because iodine is used as a disinfectant for wounds. Red phosphorus you can obtain because it's present in the heads of matches, so you can scratch it off the match heads and use that, and hydrochloric acid can also be obtained. So, in some countries, particularly Russia, drug addicts are taking codeine-containing medicines, cooking them up with this appalling brew here to make something very potent because it contains desomorphine. In Russia, this is known as crocodile. The reason it's called crocodile is that when it is injected into a vein, it causes enormous damage to the tissues. The damage is probably not caused by the desomorphine, but is caused by all the other chemicals and byproducts that are produced in this reaction. The skin becomes hard and scaly, like the skin of a crocodile, hence the name crocodile. There are apparently many users in Russia. It's extraordinarily addictive, and once people start taking crocodile, they will take it continuously until perhaps they run out of iodine or red phosphorus or cough mixture. Most disturbingly, crocodile now seems to be spreading to other countries around the world, including the United States. Now let's look at analogues. Here again is the structure of diamorphine, which, as you know, is an analogue of the natural compound morphine. Diamorphine is illegal. Now look at this compound here. That's not diamorphine. It has one extra carbon atom, so chemically and legally it is not diamorphine. But it would be just as effective as diamorphine because the two ester groups that have been added would be cleaved off in vivo and morphine would be released and have its normal effect. So if you make diamorphine illegal and you specifically say diamorphine is illegal, diamorphine is diacetylmorphine, this chemical here, just as effective, would not be covered by that legal definition. How can we deal with this issue? In principle, illegal chemical laboratories could modify drug molecules in very simple ways to avoid the law. So as long as these illegal laboratories stay ahead of the law, then these so-called designer drugs are perfectly legal. What are the solutions? One solution is to control specific compounds as they become a problem. When the drug control agencies find these compounds on the street, then they can go back to the lawyers and the politicians and have them made illegal. that, of course, takes time. You could control particular classes of compound. So instead of saying a compound is illegal, you could say all compounds in this class are illegal. So in the case of heroin, diamorphine, all esters of morphine were made illegal in most countries many, many years ago. Ban the whole class. The danger of this is that in banning the whole class, you may actually be banning something in there that is useful. So as you saw, some countries maintain exceptions. The UK, for instance, still allows heroin in very specific situations. The other possibility is to pass a law specifically banning analogues. So you could pass a law saying this compound is illegal and all its analogues are illegal. The difficulty then is defining what is an analog. In particular, you have to find a way to define analogues which is understandable by the legal profession. So what is understandable as an analog by a medicinal chemist and by a judge in a court may be completely different things. For instance, dimethyltryptamine, DMT. It's a naturally occurring compound. In many countries, including the United States, it is illegal. What about DET, diethyltryptamine? It's a synthetic compound. It differs from DMT in the fact that it has 2 additional carbon atoms on the substituents on the nitrogen. Well, looking at the 2 structures here, I think any reasonable person would see they are very, very similar, and DET must indeed be an analog of DMT, and under the Federal Analog Act, DET would be just as illegal as DMT. What about this one? AET. And you can see it's very similar to DMT, but it's different because the atoms around the nitrogen are different. So AET, alpha-ethyltryptamine, is a synthetic compound. As an analog of DMT, is it illegal in the eyes of the law? Well, DMT is specifically controlled. DET, even though it is an analog, is also specifically controlled. What about AET? Is that controlled because it's an analog? Well, probably any medicinal chemist looking at the structure would say, yes, AET is an analog of DET. But when this went to district court, the court said, no, the structure is too different. In the eyes of the law, it's not an analog. And so that case was dismissed, but now AET is specifically controlled. So modern synthetic chemistry has given us lots of compounds with remarkable properties, and we've benefited from them in terms of the pharmaceuticals now available to us. But we pay the price because it also gives an opportunity to the makers and sellers of these illegal drugs. So if a sample of an illegal drug is seized in a raid or is discovered being smuggled at an airport, and the investigators find, for instance, a white powder, how do they detect and identify the illegal drugs? Well, there's a number of chemical tests that can be done, and these are based on treating the unknown sample with chemical reagents and looking for particular color changes. For instance, the Marquis test gives a red-purple color from heroin, an orange-brown color from amphetamines, while the Scott test gives a blue color for cocaine. But as we know from the lecture on identifying particular compounds, we really have to turn to chromatographic and spectroscopic methods to really prove what these compounds are. For instance, we can use thin layer chromatography, which we talked about in the earlier lecture. But we know that thin layer chromatography is not very precise, and if it's used, can only ever be a presumptive test. What we need to do is to use more sophisticated instrumentation, the more sophisticated chromatographic methods that we talked about earlier, for instance, gas chromatography and HPLC. For identification of the compounds after the chromatographic separation, we would use the infrared, and particularly looking at the fingerprint region of the infrared spectrum. Then the other technique for identification we can use is mass spectrometry, and as you saw in that earlier lecture, we can combine mass spectrometry with gas chromatography and do GCMS. One of the ways that is used to detect and identify a drug in a body fluid such as urine is called immunoassay. And this involves generating antibodies to the drug and setting up the immunoassay in such a way that when the substrate, for instance, cocaine or amphetamines or morphine, binds to the antibodies, this chemically triggers a color change. And that color change can be very quickly and simply observed by the investigator. Well, these techniques, the immunoassay techniques, have come in for a certain amount of controversy, partly because of their very, very high sensitivity. Perhaps that sensitivity can be too high, and if not used properly, can give very misleading results. For instance, morphine. There are immunoassays available for the detection of morphine in urine. So the assumption would be if that someone tests positive using this method, then they must be a heroin user. But it's not necessarily so. Morphine is produced by the plant Papaver somniferum, and this is one of the poppy family. It turns out that almost all poppies produce morphine, but all the other types of poppy produce it in very tiny amounts. And poppy seeds, of course, are used to flavor, for instance, bakery products such as a poppy seed bagel. So if somebody eats a poppy seed bagel, there will be trace amounts of morphine in their system. Not sufficient to have any effect, but if the immunoassay test is not done properly, it can be sufficient to give a positive result. So someone may be condemned as a drug user, whereas actually they just had a poppy seed bagel for breakfast. So if we sum up what we've learned in this lecture, there are three types of illegal drugs. Natural compounds, which are extracted directly from the organism that produces them, such as morphine, cocaine, and cannabis. There are semi-synthetic compounds which are obtained by chemical modification of those natural compounds. An example would be heroin. And then there are the purely synthetic compounds which are made by chemical means, and an example would be ketamine. All of these can be detected and determined using the techniques of spectroscopy and chromatography that we learned about in our earlier lecture.